Okay, so it's 5 to 9, and I think most people are here. So let's start slightly early. The school has one aspect that is computational, and I know that there are some people here who are the experts, who know all the things I'll tell you today, and there might be some people who have never written a program. Now those who have never written a program, they can admit it now. Who is that? So yes, we have a few who've not written a program, and we have some who have written a program for 20 years. Now that of course is a challenge, but I know in Boulder the students always ask questions when there's something they don't understand, so just ask questions and questions and questions. I have lots of material to cover, and so I might move a bit too fast unless you stop me and ask questions. So the first topic will be the quantum Monte Carlo, but before we go to quantum, I want to mention what is Monte Carlo integration. And to start let's start from the integrating functions using a simple rule, like the rectangles, the solid rule, or the Simpson's rule. We have a function, the red line here. We have the interval, which we divide into some, the small steps, and then we approximate the integral by sum. Signal vanishes.
Maybe under the table.
So that should work. So, what is the error here? That you simply get the rectangles, it's 1 over n with point value full 1 over the n squared with Simpson rules for your 1 over and to the form, so it converges pretty rapidly. But now what happens when you go to 2 dimensions, 3 dimensions, 4 dimensions, a million dimensions? Then this becomes very slow and bad. Because in 1 dimension, it scales like the number of points to the minus 4, but in d dimensions, we need m to the d points. So the scaling with the number of points goes like n to the power of minus 4 divided by the dimension. And so for the phase space, you have the integral with the million particles, where we have 6 million dimensions. Convergence is extremely slow, and essentially integration with a fixed mesh stops working. What can one do? There was the idea by Ulam. He was sick in bed in the 40s, in hospital. He played solitaire, and he asked a question that was just as hard. Namely, what is the probability to win when playing solitaire? There are 52 factorial games, and it's very, very hard to calculate what is the exact probability to win. And you can never, not even on the fastest machine, play all the games and get the exact answer. But he was in bed, he was sick, he was bored, and he played it 100 times. He won 15 times. And so he knew that while he doesn't know the exact answer, he knew that it's somewhere around 15% just by playing it 100 times. That was the birth of the Monte Carlo method. When you can't enumerate all the possibilities, just take a small random sample. Like, how can we calculate pi using the Monte Carlo method? We draw a square on the ground, we make a pond, which is the quarter circle, and then we throw stones into the square, and we count how many stones fall in the water. That way we get an estimate for pi quarter. That we can do in the afternoon. If CU has a pond like that, or that's a bigger pond. Now, more formally, we have some the integral over the function. And now instead of placing the points on the regular mesh, we place the points randomly. We draw some random points. We evaluate the function at those random points instead of on the regular mesh, and we get an estimate with an error. Now, is there anybody here who has done the calculation why the error scales with 1 over the square root of the number of points? So let me show you that calculation. So we have some function here, and we calculate the mean. Let me call that f bar. That mean is the sum over all, or let me call the points xi and yi is f of xi. And I want to know the average of y. So what is the expectation value of y? It is just this integral over f of x dx divided by the size of our area. What is our sample mean? The sample mean I call y bar, that is 1 over n, call it n here, m, and sum over I equal 1 to m of f of xi. Now what is the difference between the sample mean and the true expectation value? So let me calculate the expectation value of y bar minus the true sample mean. And that is just the expectation value of 1 over m, sum I equal 1 to m, f of yi minus the expectation value of y. Now we know that calculating the expectation value is linear, so you can just write that as 1 over m, expectation sum of I equal 1 to m, expectation value of yi minus the expectation value of y. This is just the expectation value of y. So this drops out, and we get out that the expectation value of the sample mean is just the true average. But what is the error? The mean deviation is 0, but what is the mean squared deviation? Let me next calculate the mean squared deviation. And that will give us the error. So let me calculate the expectation value of y bar minus expectation value of y squared. And that gives the expectation value, and now I just have to write this square. So this gives us the expectation value of 1 over m sum over I expect of yi minus the expectation value of y squared. If I multiply this out, then it gives me 1 over m squared, the sum over I x yi squared minus 2 over m sum over I yi times expectation value of y plus expectation value of y squared. This is all linear, so let me again write this down. This gives me 1 over m squared, expectation value of sum over I yi squared, minus this 2, this gives me 2 over m, sum over I equal 1 to m, expectation value of yi squared, plus expectation value of y squared. The sum drops out against the 1 over m. Minus 2 plus 1 is minus 1. So I get here 1 over m squared, expectation value of sum over I yi squared minus expectation value of y squared. Next, I multiply out this product here. And what I get here is 1 over m squared, sum over I and j, yj, minus expectation value of y squared. Let me put it into the parenthesis here, expectation value. Now what do we get here? Next, these samples that draw the xi's, they should be independent. So now assume that they are independent, and that means that the correlation will be 0. So yi, yj minus y squared, expectation value y squared, or yi, yj expectation value, which is the same, that is 0 for I not equal j. So the only thing that is left over here is a 1 over m squared, expectation value of sum over I, expectation value of y I squared minus expectation value of y I squared, because the mean value is the same for all I can drop the sum against one of these 1 over m's here, and to find that the mean squared error is just 1 over m times the variance. So that the error will then be the square root of the variance divided by the number of samples, and that will then go like 1 over the square root of m. Simpson's rules went like 1 over m to the 4th power. In 1 dimensions, in d dimension, it went like 1 over m to the power of 4 divided by d. So when the dimension d is larger than 8, then Monte Carlo wins out. The moment you have an integral in more than 8 dimensions, picking your points randomly will always be better than any regular mesh that you can place on it. If we have the physical system, the classical particles, we have 6 million dimensions, and Monte Carlo wins by far. So starting with 3 classical particles, Monte Carlo is better than the direct integration. But now, most functions we have in physics will be sharply peaked in some region of phase space. It will not be that the function is large, everywhere, but it will be sharply peaked, so the variance will be large, and the error will be large. What do we want to do when we have such a function? That sharply peak in one region. Then we simply do not want to sample uniformly, because we sample here and here and here, and we always measure essentially serial. Maybe once in a year, by chance, we meet the center and say, hey, we got something. So in that case, you want to sample more where the function is large, because that's wasted here. So what we do is we rewrite the function. We don't sample uniformly, but we choose the points with the probability distribution P. That should be similar to the function we want to sample, like the blue curve here. And then we don't measure f, but we measure f divided by p. So it's the same integral at the end, but we draw more points in the region where the function is large. So we will be more efficient. The variance of f divided by p will be smaller. The error here will be smaller and it works better. But what we have to be able to do is we have to be able to draw points with that distribution p. And that can sometimes be very hard. So let me come to the next point. How do we get random numbers? Who of you here has ever created a random number? What did you do? You used an algorithm to calculate a random number? Yeah? Yeah.
Before you know, I didn't understand why is it f over p? Why that combination?
Why? Because now we measure the f divided by p. That's the quantity we measure. Because we want to have that. We want to have still the same integral over f.
You want to do the fact that you now have a.
We bias the sampling and we have to undo that.
Okay, you
Correct. In most physical integrals, it will actually look classically like an integral dx. Now some quantity like a, the energy, magnetization, whatever, times the exponential of minus beta times the energy of x. In this case, that's the quantity we measure, and then it's the variance of a if we sample with respect to this Boltzmann weight. But we don't have to sample with that weight. We can sample with any weight we want. So, those who have generated random numbers, who has used an algorithm to generate the random numbers, and who has not used an algorithm to generate random numbers? Now, those who used an algorithm, what you've done is actually you ran a deterministic program. And once I know which method you use, I can predict which number you get. Is the number random? If you can predict your next number, then it's not random. So the problem is, generating random numbers is hard. But you've all generated random numbers. Who have thrown dice or played roulette or something like that? Playing dice is some physical process where we think it's random because we don't know the initial condition. But we all know one experiment in quantum mechanics that should produce random numbers if quantum mechanics is correct. We can take a light source, a semi-transparent mirror. We have two detectors here, and we can check whether the photon goes to the left or goes straight through. That should be completely random. You can buy this. It costs about 1,000 euros. It's a nice small box that you can hook up to your laptop, and it works. It produces random numbers. We tested it, and the numbers weren't really random. The problem is, once a photon hits a detector, the detector goes dead for a while, and afterwards, due to the photon bunching, it's more likely that it sees a second copy of the same photon. So you have to wait a long time until it's back towards the rest state. And so instead of 4 megaseconds, you get at most 1 megabit/second, but most about 30,000 random numbers a second, while typically we need about 1 billion random numbers a second. So it's very, very hard to get true random numbers. What we thus do is we use pseudo random numbers. They're generated by an algorithm, which means they are not random at all. There's absolutely no entropy in that sequence of numbers. It is completely deterministic, but if I don't know which random number generator you use, then it might look like it's random. It might be good enough. But we can never trust it, because your new algorithm that you wrote, your program, might just be the first program to detect that those random numbers here are not random at all. This might just be the test that's needed to find that those are not random numbers. So that's a big problem that happens once every 5 years. We get the results which are wrong, and then it turns out it was not a bug in the code, but it was bad random numbers. Then we switched to some new generators. What did one use in the past? The simplest was the linear convergence one. We take a number xn, some random seed that we start from, like 1, for example. We multiply it with a constant. We add the constant, you take it here to modulus prime number word size, and then we get our new random numbers. If we choose the numbers wisely, then these are numbers that look pretty random, but if it's modulo 2 to the 31 minus 1, and it only depends on one previous number, then it means after 2 to the 31 minus 1 numbers, we get back to the starting value, then the sequence repeats identically. On your laptop, you can create about half a million numbers a second, meaning in 4 seconds or less, the sequence is exhausted. If your code should run longer, then that's not a good generator. So what did one use next is things like logic sequences. You take a big buffer. In the past, we had some choice of about 50 numbers, 800 numbers. They are all bad by now. So you take the buffer of 2,281 numbers, and you say the next number is the one that is 1,252 steps back, plus the one that is 2,281 steps back. That has the long periods. You will never exhaust it. It vectorizes nicely, and so on. So it's very fast. But when you run simulations long enough, there's also a bad generator. You realize this is not fully random. There are some generators like the Mersenne twister or the well generator that are better. They're slower again. But so far in a simulation, we haven't seen that they produce non-random numbers. In careful tests, you see that also those numbers are not truly random. But in your simulations, that didn't show up yet. Yes?
Can you elaborate a little bit more, like sort of quantitatively, like is there some metric on what's good, what's not good?
The metric is your simulation at the end. If the result you get in the error bar agrees with what it should be, then it's a good generator for your application. If the result doesn't agree, and bad means there were cases when an Ising model, the energy at the critical point came out wrong by 40 error bars. That's really, really bad. But in some simulations, it comes out perfectly okay. So the true metric is no pseudo-random number generator produces any entropy. The numbers are never random. If you know the generator, you can always predict the next number. So we have a test that shows you exactly that you know the next number, so you know that none of these is good, in principle. But maybe it's good enough for your simulation. The only thing you can do, if you see some new physics in your simulation, change the generator. Take a new type of the generator, run it again, and if the same physics shows up again, then it might be real. If it goes away, then it was just the generator.
How does it impact what you described, let's say, in the simplest version of evaluating the areas of these integrals?
Yes.
How does it, the fact that it's not exactly random, how does it impact them?
It might have some bias. It just gives...
You miss some of the areas or something.
I weigh some regions more. Well, there might be bigger the correlations. The correlation term here might not be zero. So then I just get the wrong result, sometimes. Once in 5 years. If I use the bad generator. When I use the best, then it may be only once in 10 years. But then I know that that generator which was the best so far is bad for this simulation. True random numbers are just far too slow at the moment. So that's one thing we have to live with. You always have to be careful, and you should always publish which generator you use for your Monte Carlo simulations.
I mean, don't you have like in practice, don't you have a random number generator that you use that you've never experienced a problem with in Monte Carlo?
Oh, there is. It was the like Fibonacci until the first problem appeared, and then we switched to the Mersenne twister. Now we have to continue.
So have you ever found a problem with the Mersenne twister?
Not yet. So far, that's what I would recommend to use. The Mersenne twister or the Welsh generator. The Japanese, the Canadian there.
But in what sense is one better than the other?
Speed, right?
Well, let's say the speed is not. I mean, like, so is it better because it has these correlations that only come up in some high order?
It's better because it has. Okay, so the really good ones are the graphic ones. What it means there that if you can predict the next number, if you find any correlation, then it means that there is an NP hard problem that you can crack. So those generators are very, very slow. So you want to just find a hard problem, and if you then find the correlation, then it means there's a way to solve that hard problem, which would be exciting. We tested those generators, they produce about 1 megabit a second. So they are also about a factor of 10,000 too slow. So we want one that just is good enough. But it's a hard problem that you have to solve to predict it, but it's not very hard. So that's this trade-off between speed and quality. So how can we test for it? I think that's the question. What is the quality? So first of all, we know these numbers are not random. Are they random enough? That is a maybe. And one does many tests for those. Is the distribution uniform? Are the correlations with distance 1, 2, 3, 4, 5, 6, 100, and so on? There are many tests, and when you pass all those tests, then the question is, are these tests enough? And the answer is no, because your calculation might just, in a subtle way, depend on the correlations in the generator and give wrong results. So the only way is you run your simulation twice. If it agrees, it's a good one. If it differs, then it's a bad generator. The tests that exist, there's a long list. Called the birthday spacing test, ranks of matrices, there's a monkey test, and there are many subtle tests that people invented. And most generators failed those tests. Once it fails it, it's out. Those we use are those that pass those tests, or that pass most of those tests. But even for the Mersenne twister, there's about 3 tests which it fails. So what should we do? Should we run our program get 1,000 times slower and use one where we know that it didn't fail yet in any test? Or should we use one that seems to be good enough, like the Meson twister? So far we're using some that are just good enough because they didn't fail any physics tests so far. But for any of those generators we use, I can show you a test that it fails. We have some ideas of how an entropy source could be used to make number pairs truly random, but that's not yet really working fast. So, random numbers are hard to get. And you always have to keep in mind when you get a result that's exciting, first check whether it's not just a bad random number, the generator, or a bug in your code. So far we got the uniform numbers, the generators, that's in the range from 0 to 1. What if we have a range from the A to B? We simply scale it. That's easy, as long as it should be uniform. But what if you want non-uniform numbers, like this Boltzmann weight here? There's one way which is called the inversion method, which relies on the fact that the probability for a number x to be less than a value y with the distribution f is just the integral of the distribution from the start up to y. Right? And similarly, that is also the probability for a uniform number to be less than that integral. The probability for a uniform number in the interval from 0 to 1 to be less than 0.8 is just 0.8. So the probability for a number with the distribution function f to be less than y is the same as the probability for a uniform number to be less than the integral of the function f up to y. We can use that to identify the f distributed number x with the inverse function of the integral of the distribution here, the function f evaluated at a uniformly random location. So for any distribution f, if you can analytically integrate and invert it, you can get an f distributed number that way. For example, for an exponential number, it's just minus 1 of the lambda times log of 1 minus a uniform number. That's the equation you need. Next trick, how do we get Gaussian or normally distributed numbers? There's no closed form nice solution for that Gaussian integral that can be inverted in 1 dimensions, but in 2 dimensions we can do it. In 2 dimensions we just have the integral with dx dy, so the exponential of minus x squared plus y squared and a prefactor of 1 over square root of 2 pi squared. This I can rewrite as integral from 0 to 2 pi d phi, integral from 0 to r dr.
Can you put on the light, please?
Yeah. Now I have an r times exponential of minus r squared. This I can integrate. Because what this means is just that r squared has an exponential distribution, and the angle phi is uniformly distributed. So what I do is I draw a uniform number u1. I calculate from that an exponentially distributed number for r squared. So this is integral with dr squared exponential of minus r squared. That is this minus 2 times log of 1 minus u1. Then I take the square root to get r out. Then I multiply it with sine of a uniform phase for the first number and with the cosine for the second. So getting two uniform numbers, I can, using the Box-Miller method, get two normally distributed numbers out. It takes some logs and sines and cosines, so it's not really fast, but it works pretty well. What do we do in general? In general, if we have a function that we can integrate, that we can invert, we use the detection method by von Neumann. And what we do here is we draw our distribution functions, and it needs to have some maximum. What we do now is we draw a random number somewhere on this axis. Like here. Now that was drawn with a uniform distribution. But the true distribution has this shape here. So now we draw a second random number between 0 and 1. Let's say that one here, that u number here. And if this u is less than f divided by the maximum here, then I accept it. If it's bigger, then I reject it. So here I reject it. And too big, boom, it's gone. So I try a new number. Let's say now I try a number here. I draw get the uniform one. Now it's below that ratio, so I accept it, and that's the number I use. So that always works. That works with any linear distribution in a function that's bounded. But if the small part is big, then it can be very, very inefficient. Like, how would you draw random numbers in a sphere? You might take a cube, get the random number, and pick a number only when it's inside a sphere. In 2 dimensions, that probability is the pi quarter. In 20 dimensions, that probability is about 10 to the minus 12. In 100 dimensions, when you pick a random point in a cube, it will never lie inside a sphere that's inside the cube. So that works in principle, but it can be very slow. So now, what do we do for the physical problems? Because here, when we take the Boltzmann wave, we draw some random position here for the particles, we get a very unlikely clear configuration, so it will essentially always be rejected. The solution is the Metropolis method. What is the Metropolis method? Is essentially just what I sketched before. We want to calculate some integral over the phase space with some way PFC. There might be the Boltzmann weight normalized by the position function. We want to measure some quantity A. we draw the configurations randomly with a Boltzmann weight, and we measure the mean value of the sample I draw. So that way we can sample any physical system. And what is the challenge? The challenge is just picking the configuration C with the right distribution, namely according to this Boltzmann weight. Why is that hard? The first reason why it's hard is because we don't even know what C is, so we can't even normalize it. If we knew that, then still we can't really invert this function, integrate it, invert it. There's no easy way of drawing configurations with that distribution. But if we solve this problem, then we have essentially solved the key problem in statistical mechanics, because then we can just sample clear configurations and get the answer with a small error bar. And there was a list in the year 2000 of the 10 top methods of the 20th century. And the top one on that list was the Metropolis algorithm. Why is that the most important algorithm invented in the last century? You get that when you read the paper. Who of you here has read the paper that is not from my group? So, 2 people. Who has heard about the Metropolis algorithm? Now, that's one of the most important methods, and you haven't even read the paper. It's really worth reading the paper for a few reasons. The first is, it was written in June of 1953. And the title is Equation of State Calculations by Fast Computing Machines. What happened back then? Metropolis built a fast computer. It ran at more than 1 kiloflop. It could do 1,000 operations per second. And they built this big machine, and Los Alamos and called it Maniac. Maniac was used just to show people how such the acronyms are useless and should be stopped. It didn't really help. But the main problem they had was they had this big machine and they didn't know what to use it for. We had similar problems recently, and that's what Schultes will tell you about later. So, Metropolis asked to tell her what could we do with this the fast machine, and he had the idea that one could mix the sampling idea by Ulam with the detection method of von Neumann and use that to sample physical systems. And he asked his postdocs, Ariana and Marshall, the Rosenblut, to write the method. Ariana developed the method, and her husband coded it, and there's the Taylor's wife here. She ran the program on the machine then. And what was it all about? When you read the first sentence, this paper, then it tells you that they realized they had a breakthrough here. And the purpose of this paper is to describe a general method of calculating the properties of any substance. So they say they have solved this key problem of statistical mechanics. There's a sentence here that classical statistics is assumed. We solve that problem in the next days. But here they have a method of calculating the properties of any classical system, with a caveat suitable for fast electronic computing machines. The fast machines which we have now are not fast enough for some problems. So the title here is still appropriate, but for some method, some problem it works well. For some problems we need much faster machines. Now, how does the method work? Let's go a bit slower here. So basically, the idea is that instead of drawing random configurations from scratch, we make a Markov chain. That means we make a chain of configurations where we always make only a small change. So instead of drawing a random spot in the US, I just walk and I draw a random the direction. Step forward sometimes, to the right sometimes, backwards sometimes and make the random walk. If I do that long enough, then I sample the whole US. We have to be careful though. The whole thing has to be ergodic. Ergodic means I have to be able to reach any location. For example, if the doors here are closed and I walk around and I sample, then I don't sample the whole US, I just sample this room. Then I will ask you, what do you work? And then you say you do physics. And then I realize at the end that everyone in the US does physics. But that was a mistake in my calculation. The code might be right, but I wasn't ergodic. I stayed in this room. I did not reach the whole US. So, and then I have to make sure that I choose my steps in such a way that I sample the whole US with the right distribution. You shouldn't always step forward and simply walk out here. So what does this whole mean formally? We have the so-called the transition matrix Wxy. It gives me the ability to go from configuration X to configuration Y. And it should not depend on the past. So the Markov chain does not have any the history. The new configuration only depends on where I'm at the moment. That the ability to go to configuration the C2 depends only on C1 and no previous configuration. Then what do I have to have in addition? The probabilities have to be normalized. The probability to go anywhere has to be 1 in total. So the sum over y of Wxy has to be 1. Next, I have to be able to reach any configuration from any other, not in one step, but in a large number of steps. So after, for each pair of configurations, you have the x and y, there must be some pair of the steps n, after which I'm able to reach y from x. I have to be able to reach y in a finite number of steps from x. If you don't do that, then there are some states I never sample, and that's bad. That's something one has to think about with the updates once we do that. They are ergodic. Easiest to show balance. Balance means that I sample the right distribution that I want. And what do we need for that? Is that after we do one step, we should still have the same distribution. So the fixed point I run into, then is the one where the distribution is unchanged. And let's assume the distribution at step I was pi of x. Pi of x. Now what is the distribution in the next step? The next step, the distribution is pi plus 1 of y is the sum over all y of pi of x times the transition matrix Wxy. Since the ability to be in state y, and that's the sum of x here, is the sum over the all states I might have been in the last step, multiplied with the ability to go to the new state y. Now we want that reaches a fixed point, So we want to have that the pi plus 1 of x is the same as pi of x. That's the stationary fixed point. And then I need to have that p of y is the sum over x, p of x times wxy, which means p should be a left eigenvector of the matrix w with eigenvalue 1. But what we typically know is we know p. We want, for example, the Boltzmann distribution. Now we need to find a matrix W that has p as its left eigenvector. That seems like a tough problem. And in general it is. The trick of Metropolis et al. Was to find a new condition that is even stricter, that is sufficient but not necessary, but that can easily be satisfied. That is the detailed balance condition. This is the balance condition what we need, the sum here. But now I write down a more specific one, a stricter condition, namely that p of y times w of y times w of y comma x should be the same as p of x times wxy. Or here that the ratio of the probabilities to go from x to y divided by that of going from y to x is p of y divided by p of x. Why is that enough? If I take this and if I plug that equation into here, then I see that sum of the x here of p times wxy is the same as the left hand side here. This is the same as the sum over x of p of y times wy comma x. That p of y is a constant which I can pull out the front. Yeah.
Don't you also have to ensure the system's not periodic? Isn't that an additional criteria?
That's an additional criteria that I wanted to mention at the end, yes. When it's, you have to be careful that it's not periodic. What's enough for that is if for the chronicity, it's enough that you write it in a more strict way that for all x and y, there exists some n xy, so that for all n larger than nxy, this probability w to the power nxy is non-zero. That's enough. So according to the strictness means there's one point on which at any step you might have reached that point y. But we are here now. Okay, here that's a constant, so here I have a p of y times sum of x wy x. This is 1. So with the detailed balance, we automatically imply balance. What we need to find is we need to find an algorithm that satisfies this condition here. The detailed the balance condition, that the ratio of the probability to go from x to y divided by that of going from y to x should be the ratio of the weights of the states. And now for our method, what does it mean in the Metropolis method? We start from a configuration. You want to propose a new configuration, like you want to propose a step forwards or backwards or left or right with a certain probability AXY, the a priori rate. And then I say, okay, I want to step here, but now I have to check whether I actually want to go there or not. And so I want to accept the proposal only with the probability PXY. So that then we end up with a total transition rate, that is the product of the two. The AXY times PXY. Now the question is, how do I choose that PXY so that I get the right distribution? What I need to do, I need to choose in such a way that detailed balance is satisfied. And we write the WXY as this product here of the AXY and the PXY. And so what we need to satisfy in the end is that AXY times PXY divided by AYX times PYX is the probability P of Y divided by P of X. And we want to find the solution for these capital P's here. The solution due to the analogy is to just use the minimum of 1 and the ratio of A times P of Y divided by the AXY times P of X. That satisfies detailed balance is something I leave to you as homework until the afternoon. It's a very simple calculation that you should do by hand. It's very easy, it takes just a minute. You should please do that over lunch and the coffee break. It's easy, but then you see that it works. And that way now we have an algorithm that works for any physical classical system as long as we can calculate the weights, the ratio of the weights that is. So we don't need the addition here function here drops out. And we need to have some ergodic updates. And then it's enough that we can sample any physical system. For example, for the Ising model, I hope all people here know what the Ising model is. If not, you should stop me immediately. So we have an Ising model with some spins. The method is I pick a random spin, like this here. I propose to flip it. Now what is the probability of flipping it? The probability of flipping it is, we have calculated the minimum of 1 and at the ratio, no, let me not do that, of AYX times P of Y divided by AXY times P of X. What is AYX? Who can tell me what is the priority rate of going from a configuration Y to configuration X?
Y 1 over n?
It's 1 over n?
One number of spins.
It's 1 over the number of spins if the two configurations differ by one spin flip. And it's 0 otherwise, right? I pick a random spin, I want to flip that, so if two configurations differ by one spin flip, then it's the probability of 1 over n. If two configurations don't differ by a spin flip, then I will not propose it. So let's focus on the case where they do differ by one spin flip. And this is just 1 over n. This is 1 over n. So those two just cancel. Then it's just the ratio of the weights. And what is the weight? P of y is just exponential. I think you can't read that back here. So P of y is just exponential of minus beta of E of y. And so we get just here the exported child of the minus beta times the new energy minus the old energy. It looks intriguingly simple here. That is because here in this case, detailed balance turns out to be very simple because these are very simple rates 1 over n. In quantum Monte Carlo, sometimes it's very tricky and deep, and I've had people look for 2 or 3 months for a bug in the code, and then it was a problem in detailed balance. So that can be quite hard sometimes. So don't be fooled. And that's why I want you to actually calculate that for some simple models, so that when we get to some other models, that you'll know then why we get those equations. And then one thing at the end is, when we reject a spin flip, it doesn't mean we start over again, but then it means that the new configuration is the same as the old. And it means we have to measure again in that old configuration. It doesn't mean we just try something new, but it means that the next configuration is again the old one, and measure once more in the old configuration, and then try a new spin flip. That's one thing which many, many people forget. Or where many actually claim that it's actually wrong. As to when we reject it, it means just we keep the old configurations, we measure again. And know at least about 10 cases where people looked for weeks or months for a bug, and then it was just there. One last thing here is the equilibration. We don't start in the fixed point case. We start in a configuration where the oil springs might be up, for example. So the starting distribution is one where one configuration has weight 1 and all others have weight 0. So it will take a while then until we reach the equilibrium distribution, that P here. And how long that takes depends on the spectrum of the matrix here, the W. We know it has an eigenvalue 1, which is one of the fixed point distribution, but it has some others, and it's the second largest eigenvalue that will determine how long it takes to converge. So we need to run it for a while until we reach equilibrium. Now, how long should that be? That's a tough question. Who can tell me how long you should run a simulation until it's equilibrated? Should I do 10 updates? 10 updates per spin? 1,000 updates? 1,000,000 updates? Should I always wait a month or a day? Yeah?
Probably the mean value that we're measuring has exponential scale.
Yep. So we can measure running mean, for example. We look at the time series and we see, okay, that converges. So the factor is a lot and then the factor is less. Now it seems converged. So now here you would say, okay, maybe from here on we should really measure, and that part I throw away. Now sometimes you have a bad surprise, the runs like this and then it jumps. What do you do when that happens? You have to be very careful and run it even longer. And let's run it for 1 more month. Then it jumps again. What do you do now? You stop the project. There's no way you can be sure that in 2 years it will not jump again. So you have to carefully look at the time series for the new problem, because it might be that you're stuck in some local minimum, and you might not know that. So the trick for that is what you should do. You should start with a tiny system at high temperatures, because for a tiny system at high temperatures, we have a chance of getting it converged. And what do I mean by tiny? I don't mean 10 times 10 at a temperature of 0.1. I mean 2 times 2 at a temperature of 10. It might be that already there you're stuck. Then you slowly increase it to 3 times 3, 4 times 4, and you slowly lower the temperature. You carefully increase your the system size, and you carefully lower the temperature. For the codes we use, these are methods which we know are fast, they work fast, so there it's fine. But for a new project, you want to check it. Always start from a small system at high temperature. Next, we want to look at errors. How do we calculate the errors? Well, we had the equation here. So now I have some handouts here of the paper. I with your a big okay, because he had a problem. He has a nice book on time and the error of time, and there he has this nice simple model. He has two dogs, A and B, the Annick and Burnside. One of the dogs is flea-ridden, has 50 fleas. The other dog has no fleas. Now when the dogs play, then fleas jump from one dog to the other and back. So at the end of while there should be a binomial distribution of the fleas on the two dogs. And one can sample that by choosing for each flea, whether it's on dog A or B, then that's what we get, the two answer, the Monte Carlo sampling, and it's all fine. Does anybody have problems with the fact that this point here is outside the error bars? Is that a problem? Would it be a problem if all points were inside the error bars? I think we need a vote here. Who thinks that this is a problem? I'm Swiss, so I like to vote. So who thinks that this is a problem? 3. Who thinks that this is not a problem? Now, of those, is there a spokesperson that can tell me why that's not a problem?
The error bars are really like 1 sigma. So
Yes.
you expect it, say you have 10
Yeah.
different data points that a couple of them will lie
Yes.
outside of 1 sigma.
Right. 1 sigma means that about 2/3 should be inside.
Yeah.
Yes, and 1/3 should be outside. So if 1/3 is not outside, then we have a problem. Because then we have error bars that are too large. But it shouldn't be more than 2 sigma outside, because that has a chance of roughly 5%. This here may be roughly 2 sigma, in 1 point that's okay. If it's big error bars and nice smooth data, then look carefully whether you have not made a mistake. Now, he said, let's do the Monte Carlo process by having all fleas start on dog A, then they play, and then they randomly jump from one to the other. So let's make a Markov chain. Let's calculate the errors. And he got something like this red curve at first. And it didn't look like the true black curve at all. And it had a dip in here and 2 peaks. And so he asked me once, hey, I have this problem since 20 years, I always get that. And whenever I run the program again, I get the same. There's some problem with this Monte Carlo idea. So I told him, have you changed the random number seed? And he said, no, it hasn't. So we ran it again. And we found another wrong answer. What's going on here? What's going on here is that when we do a Markov chain, subsequent points are not independent. Here we assume they are independent, uncorrelated. But they are not. Because they jump only 1 flea, or take only 1 step. When I ask you, do you study physics? You say yes. And take 1 step. I ask you, do you do physics? Say yes. Yes. Because I take small steps, the results are correlated. So this calculation of the error here is wrong. We have to correctly calculate the error. Now, what could we do? Is I could say I walk for 5 days and then I ask a person. So I take many steps until I'm sure it's not correlated anymore, and then I ask someone, and then that's the salesperson, the secretary, or whatever, and I'm fine. If we do that, then it works out, but we get huge error bars. So So it would make much more sense to correctly calculate the error bars, taking into account correlations. And that's what I want to do next. I want to go there and want to correct that equation. And here what we had is, we just assumed that these things are zero. Yi by j minus yi by j averages that is zero. Now we know they are not zero. And so let me write down the term here for I not equal j. Because I want to keep this. Just black this out. So it's here that y bar minus exponential value of y squared is, I have one term, which is 1 over m times the variance of y. And then I have the term plus sum over I not equal to j. And I have the 1 over m squared. And I have this, the expectation value of yi yj minus expectation value yi, expectation value yj. Now I will simply reform you like that. The first things I do is I replace that by, so this term here, I replace by just 2 times sum over I less than j. That's still exact. 1 over m squared and the same thing. And next, I'll call the difference between I and j t. So write that as 2 sum over I equal 1 to m, the sum over t equal 1 to m minus I. Then I have 1 over m squared of relation with yi plus t minus expectation value yi or y expectation value squared. Next, I assume that my simulation time is much, much longer than any correlation in the sequence. So I assume that once I get to m, essentially the correlations will have died out. And I know that because I know that in the Markov chain, the correlations decay naturally, so when I run it long enough, it will die out. Because this here goes after like exponential of minus some constant lambda times t. So I replace this upper bound here by infinity. Now I want to have this sum of the relations here. And this quantity here, so I call the quantity now of the sum over t equal 1 to m of yi plus t minus expectation of y squared. This quantity normalized by the variance, then I call the integrated autocorrelation time tau y integrated, which is roughly the integral of that function here. This is defined as the autocorrelation time. When I plug this back in here, then this here is a 2 sum over I equal 1 of the sum. So 2 sum over I equal 1 to m. And I have a 1 over m squared. And I have the variance of y multiplied by this tau y integrated. The sum goes away with the square here. So I get this extra term here, 2 times variance of y divided by m times tau integrated for the quantity y. So now plug this, and when I now something of the sum of the terms, that again the total error turns out to be, when up here, the error bar gets the square root of 1 over m times the variance of y times 1 plus 2 times tau y integrated. Have this extra term here, the error gets larger. And that was what was wrong in the first picture. The error bars were too small. If you calculate them correctly, then it all works nicely. So instead of sampling only once every millions of steps when I get the uncorrelated, I use the equation for correlated samples and calculate the error that way. But you might ask now, how do we calculate this tau here? One way is that we store all the values of the time series, and they calculate tau. But it takes a long time, and it takes lots and lots of memory. What if we measure, shall we have 1 million quantities for 10 to the 12 time steps? We have 10 to the 21 numbers to store. We can't do that. We don't want to do it. But there's a much simpler way of doing it. And that is called the binning analysis. We start from our time series here, and we calculate the error naively of our raw time series. And that we know gives us an error that is too small because we ignored the autocorrelations. So the next is we always average two neighboring values. We bin two values into one bin and get that average, that one, that one, that one. Now we have 8 values that are averages of 2 values. And we again calculate the error of these 8 values here using the naive equation. Again, the values are still correlated, but now they're less correlated, and so the error will be less wrong, but still wrong. Next, we take the mean value of 4, then of 8, 16, and so on, and we increase the bin size. And the bigger we make the bins, the smaller the correlations between bins will become. So when we then plot the errors that we get as a function of the binning level, then the errors go up. And you will see tomorrow for some classical Monte Carlo simulations. When you do those local updates in the icing model, then on a small system, the error will converge at some point, and then that's the error we take and accept. For a big system, when we do this, the error will just go on increase and increase and increase and increase and increase and increase. That means we have a problem, because the data never becomes uncorrelated. So that way, we get both the right error, and we see whether the data is uncorrelated or not. And you only need about log n memory for this whole thing. So it's log n times the so it's the log n memory per measurement.
Why do you choose bins of 2 in this case? I mean, could it be that you choose A1, 2, and 3 and average them together?
You could also do 3 all the time.
Yeah, there's no specific reason though.
There's no specific reason. No. When you do 3 at a time, then you only need log n base 3, so you need less memory, but you get fewer points. Base 2, I think, is fine here. Because we still want to have about roughly 10 or 20 points here to see it here. 2 to the 20 is a million, that's what we might sample. Typically I take maybe 10,000 samples, so it's 2 to the 13 or so.
Well, this goes from 2 to 4 to 8.
Yes,
so
you could go from 3 to 9 to 27.
Yeah, so you just have more points in between.
I have more points in between here, and that helps me check for convergence. Base 3, I have fewer points. I need a little bit less memory, a little bit less time, but I don't care about this log factors, about the base of the log. Yes, but 2 or 3, or any is fine. Yeah?
understand the part about you say when the system is large, it's not converged. Like,
The system large, what I see here is that when I do the spinning, the higher I make the level, the larger the error becomes. And the true error is once that level is out and you have got the conversion. Because once the bin size is larger than the correlation time, then the errors will be the true errors, because now there are no correlations left in the system. And from then on, you will always get the same true error bar. So it just converges. Here, it just keeps on increasing. So I need to run it much longer, then at some point it might converge, which might be a millennium. Let me show you now quickly why that's so slow. I have here a simulation of the icing model. The solution is a bit low, but I think we can still see things. Now I run an icing model. White squares will be up spins, black squares will be down spins. I run it at a low temperature of 0.1 of Cc, and you see it's just white. Nothing happens. I propose to flip a spin, it's rejected because it's too cold. Let me increase the temperature to 0.5. 200 times 200 system. You see some fluctuations going on. Some spins can be flipped. Increase the temperature, it's no longer perfectly aligned. Let me increase the temperature further to 0.9 of Tc. There are more fluctuations. Let me now go to 10 times Tc, and it is disordered. Wonderful, we see just the physics of the icing model. And now let me cool it down again. Let me cool it to 1.2 times Tc and define some going domains. 1.1 Tc. Let me stop it for a while. Let's see some bigger domains grow. The system becomes critical. The correlation length grows. Now let me go to 1.02 times Tc, slightly above the critical temperature. And you see large fractal shapes appear, it becomes critical, the correlation length diverges, the correlation functions become the power laws, and the shapes become fractals. But now we also see that things get slow. I do these local updates, I flip my local spins, thousands of them per second, but these big shapes, like the big black domain, the big white domain here, they are not really affected by these more local changes. The physics happens at a scale that is much bigger than my local updates, so things slow down. Because I have this the main wall here, and that I want to move around. And that's the random walk that takes about L squared steps. So the time I need grows like L squared. I need L squared local updates per spin to change something here. That is called critical slowing down. The autocorrelation time diverges when I get to the critical point. It gets worse when we go down to lower temperatures. Let me cool this off now. 0.1 of Tc. And some parts are white, some parts are black, and it will take a long time for this to turn either black or white. We could wait now until after lunch and nothing much will happen. Because this small white one here will vanish, and with the rest will take forever. And that's what we saw. Is on the big system with the local updates, the autocorrelation time is enormous. It's huge. And we even had a problem. Let me just cheat here for a second. We had a problem even here, because here we should have called out and said we have a problem here, because we essentially know they got it. At low temperature, the ground state, all spins up or all spins down have the same probability. We only sample all spins up here, because the time to flip all those spins up to all spins down is longer than the age of the universe. It will just not happen. Because you have an exponentially long autocorrelation time here. That's why we need fast computers. Yeah.
So why do you call it a problem? That's what's happening in reality.
I call this a problem because I want to sample a phase space average. And I'm stuck in one broken symmetry phase. But now you know, when I find a system, there shouldn't be a broken symmetry. Now, if I want to sample an Ising model in the ordered phase, then I think that's fine. If you want to study the dynamics of an Ising model, then it's fine because the physical dynamics is that of local spin flames. But if you want to study then the quantum system, then the physical dynamics is not that of the Monte Carlo. So I'm stuck in a process that is not physical. And then it's a problem. Close to the critical point, it's also a problem because when you get close to the critical point, then the spins can flip even below Tc, which is not the physical thing you want to investigate. So this is a process that gets stuck, but it's not the physical process. Now let me go back to the talk. I just have one last topic there. So this is now when you use the Alps code, when you look at the result files, it will tell you that the error is not converged, and it will mark it in red and tell you, hey, there's a problem here, look closer. The error bars are not converged. You have to run it much longer. This is now again the dog and fleece. The Markov chain process with the right error bars can calculate in the right way, and now there's a nice agreement. No problem is fine with the pinning, it all works out nicely. We have two more topics. The one is what about correlated quantities. We want to calculate the specific heat. Classically, it's the E squared, the average minus E squared average, or the cumulant ratio. Here the problem is when you measure the energy E or E squared, the two measurements are correlated. When E is large, then E squared is also large. When E is small, then E squared is also small. So here, this error and that error, you can't just take the uncorrelated because they are correlated. So what does one do there? One thing you could do is you could run the whole simulation 10 times. Or you could take your the time series and you split it into M segments. Or you run the M simulations. You measure X and Y, and then calculate some function U of X and Y. You might calculate it for the first pin, the second, the third, and so on until the mth pin, about 30 or 60 pins or so. Then you calculate the mean value of this U and the error of that U quantity. That works out nicely. That's the right way to do it, but might be when you split the long time series into the small pieces, that is noisy data. Might be that the function here is X divided by Y, and Y might then be sometimes be nearly zero and you get huge error bars. So this might be unstable. That's why one rather calculates something like the jackknife for the bootstrap method. The jackknife is the easiest here. And what that means is you take your function, you calculate it once on the whole time series. Then you calculate it once more. Now you don't calculate it on only the first pin of the time series, but you calculate it on all pins except the first. So it's pretty stable because you have all but one pin in. You have almost all your data. Then you calculate it in all but the second, the third, and on. And then you have M values where always one pin is missing. And then at the end you calculate the error from the values here, and it looks almost like the normal equation here for the error, but there's one extra factor of the n-1 in here. And then you get an error bar that is reliable. Now, of course, writing a program for that might be cumbersome. The binding and this and that. That's why most people don't do it. Many people, students I talk to, they just say, why do it? Let's just measure it. Long enough distance, or who needs error bars? Then I tell them, it's no use if you get a number like 42 and you don't know what it means and you don't know the error bar. Without an error bar, the quantity is useless. So we have some libraries in C++ and Python that make it very easy for you. You have give the class here, give the real strawberry class. You can just type in your values, then you print the mean value and the error, and you get the right error using binning and all. You get your cumulative ratio, you calculate an expression that prints the error bar using checknet. You can trust those error bars. Or in Python, there are nice scripts that can do the same. So this makes it easier than making it by hand, and you get the right error bars. We'll have the homework exercise where you get some template for the C++ program or the Python script to do local updates in an Ising model. And it's all done except what you have to implement is you have to implement the updates and the measurements and then run it. Those who like the C++ should use that. Those who have never programmed or who like Python should use the Python script and use that. It's about 4 lines of code you should write. So it's not hard, you could do that on the weekend, the latest, tomorrow night maybe. There's time for that. Now, the last quick topic. We saw that the critical slowing down happens. It was the power law at the critical point. It is exponential. The first order, the phase transition. How can I solve that? How can one overcome that? What I want to show you now as the last topic is the local updates have problems. Mostly today is the critical slowing down. And there's a smart idea, and these are the Swenson-1 cluster updates. Most good ideas in Monte Carlo are small, simple ideas at the end, but you need to have the right simple idea. That idea is, what was the energy of 2 parallel spins? It is minus J, and the 2 anti-parallel spins is plus J. So when I pick a spin and the 2 spins were not parallel, then I will always accept to flip it. But if 2 spins were parallel, then I will flip it only with the probability that is exponential of minus 2 beta J. And with 1 minus that, I will not flip it. I will not do anything. Now that were the local updates, and they were not efficient at the critical point. Now there's this small change of the cluster updates. If I decide that I don't want to flip this spin against that, because they want to stay aligned, I can do 2 things. I can either keep them and leave them, or I can say, okay, hey, let's flip both spins. When I flip both spins, the weight stays the same. So the idea of the cluster updates is, when I don't want to flip this spin against its neighbor, let me just flip the neighbor as well. What does that lead to at the end? What I then have is, also the neighbor has neighbors again, and they need to recursively continue. You might start with this spin here. It's fine with respect to that one because I want to flip it. But those 3 neighbors here, they are the parallel, so they don't want me to flip against them. So I draw a random number with probability of exponential minus 2 beta J I accept. The flip, the probability of 1 minus exponential of minus 2 beta J I also force the neighbor to flip. Let's say here that this was okay, but these 2 were not, so I flip the neighbor as well. And that neighbor again has neighbors. I have to check those neighbors. And so on. And now here still that may be okay, but here and here still have some neighbors that are parallel. I check again, and either I add it to the cluster I flip or I don't. Boom. Here I might stay okay. Over here it's still question mark. I say it's not okay. Now I have these two neighbors, and I run it until it's all done and finished. Now it's all fine. Now I flip this whole big cluster. Boom. And I did a big change. Let's look at this in the applet. Let me go to high temperatures. Let me go close to the critical point. Now let me turn on this. Let's run it a bit. Now let me turn on this cluster up. There's a bit these red clusters that flash up here. And this is much more efficient than these local updates. System size here is 200 squared, so the slowdown is roughly about 200 to the power of 2.1, so it's about 40,000 times faster with the cluster updates. These are the local updates. Now let's go to lower temperatures, 0.1. And again, it will take it until after the dinner for that to turn either black or white. We put wait, and wait and wait. Or we do cluster updates. And the cluster updates here also flip from black to white and back immediately. It's just much more efficient. But local updates are stuck. So here now, with a simple idea on the 200 times 200 system, we had a speed up of a factor of 40,000. Over the past 30 years, since the calculation of the Ising model, the speed up due to new algorithm was bigger than the speed up due to Moore's law. So if you take a computer from the early 80s and run the modern method on that old computer, you will be faster than if you use the local updates on a petaflop machine nowadays. Which means that you having new ideas is really the way to make progress, and not only to wait for a faster machine. So let me review for the last time the cluster update and then we end. The cluster updates are simply, we ask whether we want to flip a spin against its neighbor. If yes, then it's fine. If it's not fine, then we just flip the next spin as well. That means we add it to the cluster we build, and then we again ask its neighbors and so on. So we grow that cluster outwards until it's finished, and then we flip it. The local updates can be coded in about 4 or 5 lines. The cluster updates need 3 lines more. With 3 lines more code, you're 40,000 times faster. I also want you to code the cluster updates after you coded the local updates. Yes?
Do we need to worry about the arbitrary transition rates?
You have to, I simply sketched that here how it works. We have to go rates work out. I will explain that in detail in my next lecture. We will do the formal proof that this works. I want you to first see it, digest it, and then I'll show the proof next time. Any more questions? So tomorrow we will run the code for the classical the Ising model on the computer. For that you don't need to know about programming. It should be simple. You can program if you want, but you don't have to. What I would like you to do though is over the next days look at the template then that we give you for an Ising model, local update code, and try to write the few missing lines in that code. Those people who know how to program, for them it should be no problem. For those people who have never programmed in their life, they should ask us for help, and we'll help you. Python is a language that undergraduates in the first year can learn in 1 hour. So I expect that you can also learn it in 2 hours. Okay. Then for tomorrow, for the hands-on session, I want those that have a laptop to bring the laptop. Those who don't have a laptop, you can use the PCs in the computer lab. You get the software to install tonight or tomorrow. Now, who here uses neither macOS nor Windows? Linux, yeah. You will have to have a few. You will have to have a little bit more work to install things. So you might want to do that tonight, or use the PCs now for the first day. Yeah.
Can we quickly ask, who did not bring a laptop? One?
One.
Okay, very good.
Who uses macOS version 10.4 or earlier? We don't have the software for that yet. Who uses the Windows version before XP? Good, then we shouldn't have a problem. And the Linux people, I hope, are some computer gurus who know how to install software. Okay, thanks.